Let's take a look at the earliest deadline first algorithm. So the first thing we need to do is define an inversion. Inversion. So what's an inversion? So imagine you had a schedule, and over here was, was job J, and here's job I. If the deadline of job I is less than the deadline of job J, then we call this an inversion. This right here is an inversion. And there's a claim that if ij create an inversion, there exists an adjacent inversion. So what does that mean? Well, imagine you had the numbers 0, 1, 2, we're counting up. And then you had the number, let's say we had the number 4 here, and then, oops, and then you had the number 3 a little bit later down the line, and I told you that there's 2 numbers here. So 4 and 3 over here create an inversion, right? We want to go in ascending order, and there's clearly a descent somewhere. The claim is that either here or here, there will be a smaller number. So what does that mean? So in order to get from 4 to 3, either you're going to go 5, you're going to continue ascending here, and then over here, if you keep on ascending 6, there's an adjacent inversion right here. It goes from 6 to 3. On the other hand, if you had a 2 here, then there would be an inversion right here from 5 to 2. And finally, if you had a 1 here, there would be an inversion here from 4 to 1. Because if it keeps on going up, and then later on it's going to go down, at some point it has to jump from going up to going down. So wherever that point is, that's going to be an adjacent inversion. So we're saying that that definitely exists. If there's an inversion, there has to be an adjacent one. So then in that case, let's rewrite the schedule like this. Ji. Okay, and we have another claim, which is really a fact. There exists a unique schedule with no inversions. And that schedule is our schedule, the one produced by earliest deadline first. And if you think about it, it kind of makes sense. Our schedule basically selects for non-inversions, right? It chooses to pick the jobs whose deadline come first to come earlier in the schedule. That's what earliest deadline first means. So of course there's going to be no inversions in ours. And there's only one schedule that's in order of deadlines. So that's why ours is unique. It's pretty trivial. So the final thing to prove is that when you switch I and J, when you switch two adjacent inversions, or when you remove an inversion, that you don't increase the maximum lateness. And once we can prove that, we can just show that as long as there exists an inversion in a schedule, we can reduce it down to a schedule with no inversions. From there, we can just prove that if you take the optimal schedule and remove all the inversions, you come up with our schedule, and our schedule is equal to or less than the optimal, making ours optimal. So how do we prove that removing an inversion doesn't affect anything? Well, we can say that the lateness of first thing to prove is that by moving I, let's create a new schedule, which is the schedule that we hope to achieve. We want this. By moving I earlier, it's kind of obvious that that's not going to affect i's lateness, right? Because we started I earlier and we're finishing I earlier. So I is not going to grow. But by moving j later, maybe j would grow. So we need to show that the lateness of j is going to be equal to, and we'll call this I prime because it moved, and this is j prime. It's going to equal to the finished time of j prime minus the deadline of j, right? The new lateness of j, or the lateness of j prime, is going to equal to the finished time of j prime, that's this point right here, minus the deadline of j prime, or j prime. The j and j prime have the same deadline. Well, this whole statement here is equal to the finished time of I, because notice both I over here and j prime are going to end at the same time, minus the deadline of j, right? Because j prime and I finish at the same time, and we haven't changed deadline of j, so these things are equal. This statement right here is going to be less than or equal to the finished time of I minus the deadline of I. So why is that? Because we know, imagine that f of the finished time of I was equal to 5. Okay, and imagine that dj was equal to 4. We know that dj, deadline of j, is greater than the deadline of I. How do we know that? Because of the statement over here. That's what an inversion is. It means that this deadline is greater than that deadline. So let's just say that deadline of I was 3, because 3 is less than 4. Well, this is going to equal to 1, and this is going to equal to 2. So you can see that 5 minus 3, or 5 minus the deadline of I, is going to be greater than 5 minus 4 in this case, which is 1, right? This is a bigger number, so subtracting it is going to give you a lower value. So this has to be less than this. But this right here, finished time of I minus deadline of I, well, that is equal to the lateness of I. So we just showed that the lateness of j prime, or really the lateness of j after it's been switched in the inversion, is less than or equal to the lateness of I. So in worst case, our max lateness has not grown, because before it was I, and we are less than I now, if it was I back then. So that's the proof.